Hi, I'm Neha, and this is joint work with Wolfgang Gatterbauer that was presented at SIGMOD 2024. As database practitioners, we know that users can ask a wide variety of complicated questions, anything from rankings and aggregates and group bys. And the right way, the most optimal algorithm to solve these can be different based on a wide variety of factors. Maybe you have some pre-built indexes, some functional dependencies in the data, or just the kind of query. And to find the optimal algorithm, you have to take all of these factors into account. And depending on each question, you might have a different join plan that you would use or a different index that you would leverage. It's confusing. And how do you pick, right? How do you know which algorithm is the right one? Well, the good news is that as a user, you don't really deal with this. You write down your query declaratively, and the query optimizer decides how it's actually executed, and it can pick the right plan for you automatically. You could still have a problem. Let's say you computed your output efficiently, but you don't understand it at all. You were expecting something completely different. That's not good. So now you have follow-up questions, right? Why did I get this output? How do I get this output that I was expecting? What if I wanted certain properties in my output? Many of these follow-up questions have actually been studied in the form of reverse data management, and they all suggest some interventions or repairs that in your database that would have led to the output that you were expecting and help you understand your output better. And each one of these different types of questions have been studied separately, and their own optimal algorithms have been proposed. These questions all follow the same format. Broadly, they ask what change or intervention would it take to achieve a certain output X. And here, X could be a specific database or just any database that satisfies a certain property. But here again, we run into the same issue that different questions, depending on the data, can have different optimal algorithms. And since all of these questions have been studied separately, they have their own techniques and methods depending on the query and the reverse query. This brings me to our vision. Just like we have query optimizers that solve all forward queries optimally, we would like to have a unified reverse data management system that solves all reverse user queries optimally, no matter what reverse query or query it is or what data there is. In this paper, we focus on two reverse questions, resilience and causal responsibility, and indeed build these unified algorithms for both of these. Let me introduce these problems to you. Simplifying my slides. So the first question is resilience, and this is arguably the easiest reverse question you can ask. It asks, what change or intervention would it take to achieve no output? So what change do I have to make to delete all the output that I was getting? And this is already useful. You can imagine that if you wanted to diagnose points of failure, then you would find the resilience. And turns out it's equivalent to a very old and well-studied problem of deletion propagation with source side effects. The second problem that we study, that of causal responsibility, is based on the notion of counterfactual causality, which asks what minimum change or intervention would it take to make a certain tuple counterfactual. And this is based on the Hoppenpoll framework of counterfactual causality that gives assigned responsibility to various causes of an output. I will not go into more detail about this problem definition in this talk, but details are in my paper and in previous papers that suggest this problem. All right, so the structure of the talk will be as follows. I give an example of resilience and then dive into two key insights from the paper. So assume you had a table with two columns, person and movie, and the tuple was in there if a person saw a certain movie. You also had access to the buying information of people, so people go and buy items. And you also know about items that were featured in movies. So you want to see if there's a correlation between people looking at items in the movie and actually buying them then. And here we can phrase a query as a data query, but also in natural language, we're just finding people that see a movie and buy an item that was featured in the movie. This query actually looks like a triangle because of the joins. You have three tables all joining with each other. We can populate all the tables with some default information and get some output based on joining the keys that are the same. So person has to be the same value in C's and buys, and then we can join these. We also assign each tuple a tuple ID, and then each output row is essentially a combination of the double IDs that were joined together. So now recall, to find the resilience, we want to find minimum changes that we can make to the input so that we would delete all of the many rows that we have here in the output. In this example, turns out if you just took away the double F1, which was related to some product placement, you would actually take away every single output row because all of the output rows concern just this one product placement. So this is actually not very resilient at all. In general, though, finding the resilience of the triangle query, which is the kind of query we just saw, is NP hard, which means that the optimal algorithm must be exponential, providing p not equal to NP. But turns out, if you just change the query a little bit, so let's say we only care about product placements of rare items and we're adding this unary table to our conjunctive query, you can solve the resilience problem in p time. Adding more complications now, if you had bag semantics, so you allow duplicate values in your input tables, this query with the rare items again becomes NP hard. So this is confusing, and again, it's not very easy to find what the optimal algorithm is or what the complexity of the optimal algorithm is. In our paper, we present a unified algorithm for resilience, which is automatically optimal, so we don't have to deal with the confusion on the last page. So for all known queries, whether for set or bag semantics, we can solve the question as efficiently as possible. So the first insight that I want to present from this paper is how we build these unified algorithms. And before that, I will just tell you what unified algorithms are. By unified algorithm, we mean, one, something that's unified across complexity. So whether your input query is easy or hard, p-time or NP hard, the algorithm can solve all of these. This is not difficult. Even a brute force algorithm can solve all cases. The interesting part is that we guarantee exact p-time termination for all known tractable cases. So if it can be solved exactly in p-time, then the algorithm will indeed do that. The second criterion for unified is that it's unified across settings. The algorithm works for set and bag semantics. It works for all conjunctive queries, including queries with self-joins, which are usually difficult, and there weren't previously known algorithms for all self-join queries. And it can take advantage of even unspecified functional dependencies. So prior work, if you knew there was a functional dependency, you could somehow leverage it in the algorithm. But our algorithm simply acts on the structure of the data automatically. And this is what we mean by unified. Before I tell you about the unified algorithm, I will take a slight detour into integer linear programs, which, spoiler alert, is what we use. Integer linear programs are generally NP hard, but in practice there are many solvers that are highly optimized. And we can formulate all NP complete problems as integer linear programs. We should also know that there are linear programs which provide a natural lower bound to the objective of an ILP in p-time. Now, what most modern solvers do is first they solve this natural lower bound linear program, and then they go ahead and solve the ILP. You don't need to know the details of the internals here, but the key message is that if the objective of the lower bound and the ILP are the same, then you can find the integer solution also in p-time, even though the general problem is NP hard. You might have guessed where I'm going with this. Indeed, we take our resilience problem and we model it as an integer linear program, taking the query and the database as an input. We produce an ILP, solving which will give us the resilience. This sort of modeling can also model all conjunctive queries with self-joins in exactly the same manner. And you can also model bag semantics simply by changing the objective. Now, the key thing here is that this is not just any integer linear program, but one that has a rather special property. For all known tractable cases of resilience, the objective value of the linear programming relaxation and the integer linear program are exactly the same, and we can prove this. For shorthand, I will just say that LP equal to ILP, but what I mean by this is that the objective values of the linear program and the integer linear program are exactly the same. And we've already seen from the internals of the solvers that if this condition happens, then solvers can recover the integer solution efficiently. And what we get from this is that for all known tractable p-time cases, just putting the resilience ILP to a solver will find the resilience in p-time. So now we're left with the following problem. How do we actually prove that for all known tractable cases of resilience, the linear program and the integer linear program have the same objective value? And for this, we looked at many books in linear optimization literature that studied this case and when it happens, including this book by Shriver, which is a compendium of many criteria that lead to LP being equal to ILP. But unfortunately, even in this big book, we found no criteria that would satisfy our case. So in our p-time cases, we had constraint matrices that were not totally unimodular, not balanced, not any of the criteria that would lead to LP being equal to ILP. So we needed to go beyond these known criteria that was present in this book and others. And the way we did this, the way we showed that actually our cases are in p-time, is that we use a flow graph as an intermediate. So while usually the perspective is to find algorithms for easy cases, we already have our algorithm. We know it's the ILP, but we need to prove that it is indeed easy, and we need to prove that the ILP objective is same as the linear program. And for this, we showed the existence of some flow graph such that the flow graph has a correspondence to the ILP solution. So note that while actually solving the resilience or responsibility problem, we don't use the flow graph. We just use this in a proof and show that the solution of the flow graph would be exactly the same. And the proof relies on the Maxwell-Minkowitz theorem to show that, hey, in the flow graph, you would actually get LP equal to ILP. The case for causal responsibility is exactly the same as resilience, except we show correspondence to multiple flow graphs. Again, this doesn't impact the algorithm at all. It just makes the proof a bit more complicated. I will show some quick experiments to see how this looks in practice. So there are two queries here. We will not get into what they are. But one is p-time and one is NP-complete. And you can see the growth of the integer linear program as the size of the input increases. The p-time query does indeed scale in p-time, but the hard query scales exponentially, and this is sort of the best you can do. Interestingly, there is a different query, which is also hard, but it scales in p-time. And this sort of shows the power of this approach that while in the worst case this query is indeed hard, randomly selected experimental cases, the ILP still works pretty well. I would also like to present a different insight from the paper about automatic hardness gadgets. So let's say that you are using our unified method to find the resilience of some query over different databases, and you're always getting a slow outcome, and you get exponential complexity. How do you prove that indeed this is the best you can do, that the unified algorithm is doing the best that it possibly can? How do you show that exponential complexity is optimal for this case? In general, your approach might be to write a reduction. You would say, hey, this problem must be hard because it's the same as some other well-known, presumably hard problem, and you would prove that indeed that these problems are equivalent. But this is work, and we don't want to do that. So can we build something automatic that would automatically prove this for us and compute some certificate that shows that, yes, indeed, exponential is the best you can do? So rephrasing my earlier question a bit, how do you automatically prove that exponential is the best you can do? This is what we want. We want to take as input the problem, the query, the size of the certificate that we expect, and give it to an automatic hardness finder that will automatically compute the certificate. This is exactly what we did for resilience and for a query whose complexity was not known, and it actually worked. We found a hardness gadget. In fact, we found many hardness gadgets proving that many queries whose complexity was previously not known are actually NP-complete, and our gadget finder could not only recover all previously known hard cases, but also find new ones and giving us new complexity results. What are the ingredients for this automatic hardness finder? Well, for one, it's declarative. We just give it the properties of the gadget and it automatically optimizes the search for it. And we give this properties of hardness as a semantic specification. So we prove that 5 properties that are defined in the paper are sufficient to show hardness. So if a certificate has these 5 properties, then that's all you need for hardness, and these properties can be easily tested. To find these properties, though, you have to solve NP hard problems, and this is something that the gadget finder does as a subroutine. And hence we use something that is more expressive. We use disjunctive logic programs that indeed solve problems that are in the second polynomial hierarchy. Before I conclude, I quickly want to mention some exciting things that I was not able to cover in this talk and you can find in the paper. In this talk, I spoke about unified algorithms for different problems, and I also spoke about automatic hardness finding that helps us prove new complexity results. But in the paper, we also show a complexity dichotomy for the bag semantics case for resilience and causal responsibility. So this is the case where if you have duplicates in your input data. We also show that these problems permit more tractable cases, such as if you have a read once provenance, or if you have functional dependencies in your data, which again, need not be specified to the algorithm in advance. We also show some approximation algorithms and evaluate their performance with many different experiments. The key ideas that I would like you to take away from this talk is the idea of unified algorithms, where we're changing the perspective of building different algorithms to just having one algorithm, and you just need to prove that it's p-time. I'm also really excited about the unified hardness criterion, which permits automatic search and helps save all the time spending in coming up with reductions. There are many open problems in this space, so we looked at 2 reverse data management problems, but there are more that can be solved, and one of them I show at PODS 2024, which relates to factorizing provenance expression. But the claim is that there are many more problems in this reverse management framework that would do very well with the same treatment. We could use these approaches to build more complexity results, but the main goal is coming back to this vision of having a unified reverse data management framework that can solve all of the reverse questions in a unified manner. I have pointers to many different resources on this page, and please do get in touch if you have more questions.